Good morning. My name is Mr. Berry. I love all my students. So today we are going to talk about
Lies.
electric field. Today we are going to talk about. I like that. I like the way that came in. That was very, 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 very well done. Not even rehearsed. Okay. So today we are going to look at electric fields, and we're going to focus on what they look like. Okay. Last time we did gravitational fields, and that's kind of neat because it's a way now we can kind of compare the two. So the electric field is the area where if you have a charged particle, it's going to exert a force on other charged particles. Okay, and it's measured in it's highlighted over here. It's measured in force per unit charge. So that would be actually measured then in newtons per coulomb. But we're not going to do any sort of calculations today. We will save that for next time. Okay. The difference between the gravitational field and the electric field is, if you remember gravitational fields, we always think of gravity as an attractive force between matter. However, there is a bit of a conundrum because if you know your astronomy, you know that the universe is actually accelerating. So what's causing that acceleration is a bit of a mystery, something maybe called dark energy. I have no idea. But we often think of just gravity as something that's attractive, but an electric field can be repulsive. Because you learned way back in grade 9 that two objects that have the same charge are going to repel each other, right? So there's a huge difference there between gravitational fields and electric fields. Electric fields can be repulsive. Gravitational fields always attractive, okay? But it's nice to be able to compare the two. So eventually, like we did with gravitational fields, we'll talk about energy. We'll talk about how to convert electrical fields. We'll figure out ways to measure the amount of electrical potential energy. And just like gravitational fields, we can talk about measuring if the potential energy is increasing and decreasing. And if you remember from grade 11, like something would have its potential energy decrease if you lifted the object, right? So if I have an object that is being lifted away from the surface of the Earth, for instance, it would its potential energy would increase, and if it was being brought back down, its potential energy would decrease. And the reason is because if you if you move an object against or in the opposite direction of where it wants to go, then it's going to increase its potential energy, right? If it moves in the direction it wants to go, then its potential energy is going to decrease. So think of gravity. Gravity is going to try to obviously pull this object down. So if we move it in the opposite direction, right, in the direction it doesn't want to go, then its potential energy would increase. And you'll see when we do the questions with electric fields and measuring the energy, it's the same idea. Okay, it's just it might be a little bit more complicated, but it's pretty simple. Like for example, if I said to you, imagine you have a positive charge here, and it's generating an electric field, and you have another positive charge here. Okay, and it says the question is, therefore, a positive charge moving towards a positive charge would what? Would its potential energy increase or decrease? What do you think? Does it want to move that way?
Increase.
Yeah, it would increase because it doesn't want to move that way, right? It wants to move. It wants to move that way, right? So it's moving in a direction it doesn't want to go. So therefore, its potential energy would increase. Okay. Well, we're not going to do any sort of calculations today. I said we'll save that for next time. What's really cool is when we eventually do the calculations, you'll see that the strength of the field, the electric field, is so much stronger than the gravitational field. You're going to come across a constant when we do these calculations. The constant you'll see is a letter K, okay? And its constant is 9 times 10 to the 9. It's newtons per coulomb. What is it? Newtons? No, newton meter per coulomb. Yeah, Newton meter squared per coulomb, I think. I should know this. And if you remember for big G, it was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So K should be Newton meter squared per coulomb squared. If I remember correctly, that should be that. What's really cool is the difference in the exponents is of the order 10 to the 20, which shows you just how much stronger the electric field is relative to the gravitational field, which explains why, like if you think of like a magnet, a little magnet could hold an object against like a metal filing cabinet, like a piece of paper, and it can hold it even though the entire planet is trying to pull that paper down. Even this little tiny magnet can hold this piece of paper up against the gravitational pull of Earth. So it's a much stronger force than the force of gravity. Okay. Now, what we're going to do today is we're going to talk about what this field looks like visually look at it. But I have a bunch of activities for you kids to try out. Some of the activities are repetitive. So if you find yourself like, oh man, I answered this question already, then you're like, you know what, I already know this stuff, then don't worry about it. Just move on, okay? But it is kind of, some of the activities are kind of neat, and they're the field patterns are actually quite beautiful when you look at them. I just want to go over the rules first, and the rules for drawing the field patterns, okay? If you remember, we talked about what it looks like for gravity. Gravity is simply, an object sits in space, and it causes the space to bend. Okay, that's kind of simple and straightforward. Drawing field patterns for charged objects, electric field pattern, is more complicated. But there are a bunch of rules here that are gonna help us. The first one is we always draw the field line. So the field lines has a direction, okay? And the direction is always away from the positive charge and always towards a negative charge. And you could see that actually here. You can see it right here, okay? So you'll notice that here we have a positively charged object. So maybe that could be like an ion of sodium, and its electric field would point away, okay? And it's radially away in all directions, okay? And then you can see a negatively charged object, the field lines are pointing towards it, okay? So that's the first rule. The second rule is the density of the lines indicates the strength. So if you have like, for example, like this, of an object generating field lines like that versus an object generating field lines like this, the higher density field lines means that this object just has a stronger field, okay? The third rule is larger charges have more field lines, which actually these two, you can see there's a connection between these two. The fourth rule is at any point, the field line is a tangent to the electric field. So for example, if I wanted to know what is the direction at this point, it would be a tangent to that point. Obviously, if it's a straight line, it's just obviously just the direction is just a straight line. Okay. This is important because in our fifth rule, the lines never cross. And the reason is because if it did cross at a point, that would mean, so that what that means is if I have a field line running like this, I can't have another field line running like that, because then at this point, that would have two directions. Come on, pen, what's going on here? It would have two directions. So like, for example, for this curve, at that point, it would have a direction like this. And for the other curve, it would have a direction kind of like that. And because these are, because that point represents a vector, it can only have one direction. So field lines can't cross, otherwise you would have two directions. So these are the rules for drawing the field lines, okay? So here are just some examples. Saw the first one. This is actually what happens when you have the field lines from a positively charged object and a negatively charged object near each other. This is the pattern that you would get. You're going to get a chance to actually make some of these. So what I did was I set up a bunch of activities that you can try. Let me just scroll all the way down. Okay, all the way down. Almost there. Getting there, getting there. Okay, right here. This is just a video clip about electric field, so you can just simply watch this and answer these questions. Okay. Okay, there you go. This here is activity using PhET, which we've used a few times already. So if I call that up, did any of you have any questions at this point while I load this up?
No.
A lot of this will make sense when you start actually like playing around with the charge objects and observe the field lines. You'll see the patterns, and it starts becoming like intuitive after a while. So let's open this up. I think this is the first one. Charges and fields, right? Yeah, okay, this is the first one. It's really slow today. Come on, open up. There we go.
Sir,
Yo.
do we have to hand in the answers to those questions or to these activities? Or is it just like homework kind of thing?
Yeah, just homework.
Okay.
It's just know the answers to them.
Okay.
Yeah. Oh, I'm just trying to open this up. Taking. Okay, here we go. Can you see the screen?
Yeah. Yeah.
Okay. All right. So like, for example, we looked at this pattern. So you see the pattern that you get when you have a positive and negative charge object like near each other. So you can reproduce that here. So if I have a positive object and I have a negative object here like that, you will notice that pattern. Okay. You'll see that the lines are running out and it looks like they're feeding back in. You can see that there's a straight line at some point from the positive charge object to the negative charge object. So we can reproduce those patterns with this activity. And you can do like different scenarios. Like, what would happen if I replace the negative with a positive? Okay, you can see what that would look like. And I think I have an example right here. So the sim should produce very, very similar patterns. By the way, what's really cool about this one in particular is it kind of should remind you of a bar magnet. I don't know if you remember the activity we did last year when you sprinkled iron filings around a bar magnet. It gave you like certain pattern. That pattern would be very, very similar if you were to look at the electric field when you have a positive and negatively charged object near each other. And you can see that here too, right? This is this is the electric field for sodium chloride, because sodium would be positively charged and chlorine or chloride would be negatively charged. And you can see that it produces a very, very similar pattern to what you're seeing right over here. Okay. I just pulled that off the net, so I don't know exactly how accurate this is, but it looks like it's very, very similar to that drawing. Okay. Okay. You'll also get a chance to generate like electric fields between plates. So for instance, that means like what would happen if I did something like this? So a plate would be basically you have a like some sort of a metal conductor, so a straight metal conductor, and it produces an electric field between the plates. You can see what it's going to look like. You'll notice that in between the plates, I mean, it has to be exactly lined up, but it should look something like this, where you get like field lines that are almost running exactly straight through the plate from one side to the other. There's going to be some curving towards the end. So it's going to look something like this. You can see that here. Here's an actual example, an image of the electric field between two plates. What's really cool is, this is what it would look like if you were to visualize the electric field of a neuron at rest. If you take in biology, you know that here's your cell membrane. You can think of it as a plate where on one side you have like positively charged environment, and on the other side you have like a negatively charged environment. So the electric field would look something like this over here, very very similar to that. What's really cool about electric fields is that we all generate them. We all generate very small, weak electric fields because our nervous system generates electric fields. Our muscles generate these very tiny electric fields. We can't detect them, but some organisms can. So, for example, sharks can, and so can this sawfish. And it's called a sawfish because if you look at its what do you want to call this? Its beak? I don't know if that's the right term. But if I was to like Google sawfish, they're quite interesting. They're not sharks, but they're very, very interesting organisms. Look at that. You can see why they're called a sawfish because we'll call it what is that? The nose? What kind of call it the nose? I don't think it's a nose, but whatever. It looks like a saw. And this instrument that they have that looks like a saw is it can be used to kill organisms when it's hunting, but it's also very sensitive to electric fields. So sharks and things like sawfish, they can actually detect the electric field generated when muscles contract. We can't do that, but they're sensitive enough to do that. Some animals can actually generate very strong electric fields. So we generate electric fields, but they're very, very weak. But some animals can really amplify that and use that as a way to defend itself, but also to hunt, right? So like things like the electric catfish and the electric eel can generate very, very strong electric fields. And they say apparently the eel can generate up to 600 volts of electricity. So just to put that in context, about maybe 120 volts comes out of your outlet. But it's not so much the voltage that's the dangerous part, it's the current. So even though the voltage is really high, the electric eel shouldn't be able to kill you because it's 1 amp of current. I shouldn't say only 1 amp of current. 1 amp is still quite high, but there's about, I think, 20 amps of current coming out of your electrical outlet. So it should give you a nice shock. I don't think it'd be enough to kill you though. So anyways, like I said, is today's really more about like visualizing and just talking about the electric field. Oops, sorry, this is grade 9, wrong class. Let me go back to here. So that's why all these activities are about doing things where you put charges in different locations and you can record what the electric field looks like. What's really cool then is you can use this concept to for instance, in number 7, although I don't know how to count because I put number 7 twice. Let's fix that. Number 8 now. What does the electric field look like for example, a water molecule? Where if for simplicity's sake, we'll say that water is positively charged. and oxygen is negatively charged. I came across this really cool website where they actually really nicely draw the electric field, kind of like what you're seeing here, but just prettier. Like, there's nothing here right now. Anyways, like just it looks better, okay? And what's really cool then is you can compare what you're gonna get in your results to what you see in this video clip, okay? So this part here is all about visualizing the field. I set up another activity, but this is more for next week, because this next week we'll start looking at some of these calculations. It goes over something called Coulomb's law. That and the term Coulomb should ring a bell from grade 11. It's the refers to an amount of charge. So this allows you to measure like force using Coulomb's law. So you could look at that. This sim is back to the electric field. This is another sim called radiating charge in FET. And this is about, if I remember correctly, let's see, this one is, oh yeah, this is really cool. This is what happens if because we're assuming that the charge is stationary. So in this animation, we're assuming that the charge isn't moving. But what if it is moving? That sim will allow you to visualize what the electric field looks like when it's moving. It's kind of cool. It produces some very spectacular patterns. And there's a really interesting effect that happens when the charge moves to a speed that's very close to the speed of light. And we'll talk about that the next time, if I remember, the next time we'll meet. Not Thursday, but the next time we meet to talk about electric fields. If not, then eventually at some point we'll talk about it, because it's actually related to the next big topic, which is on special relativity. Okay. The next sim is on something called radio waves and electromagnetic fields, and it kind of gives you an idea as to how radio works. Like, how do you get an electric signal from a radio station to your home? Okay, so you can play around with that sim. Questions so far? We're good? Y'all still alive?
Yep.
Okay.
I guess we're good. Yeah.
Okay.
Yeah, good.
Now, the last one will be something that you have to hand in. So I'm not going to assign it now. Okay. I'm just going to make you aware of it, because I'd rather you work on these. Okay. These sims. But just to give you a heads up, the next one is something that you will be handing in. So I think maybe I'll save this topic for the next time we talk about electric fields. Okay, so I'm not gonna go over it today, but we'll talk about it next time. Okay. In terms of electric fields, that's really it. I did want to show you something kind of neat. I came across this TED Talk. It's from 2012. Came across it, I think maybe 5 years ago, where the idea was to use the concept of electric fields as a way to treat cancer. And it seemed really, really interesting. So I'm going to give you a chance today, if you want, if you're curious, to look at that. Keep in mind, this is from 2012. The therapy is called, it's using something called tumor treating fields. I think that's the top, TTF, if I remember correctly. That's the acronym, tumor treating fields. So it's using concept of electric fields to disrupt cancer. And the idea is an electric field is we defined it as basically the space where you have a charged object, and that charged object exerts force on other charged objects. And if you watch a TED Talk, he'll talk about how when you have, if you remember cell division, okay, in cell division, the chromosomes have to line up. And if I remember correctly, the concept is when you apply an electric field, because the electric field generates a force on charged objects, a lot of those particles involved in cell division are actually charged. So what happens then is the electric field disrupts the movement of the chromosomes during cell division. So it really affects the ability for the cells to divide. It sounds like a really, really cool therapy. Now, in terms of its effectiveness, I came across 2 articles to talk about their effectiveness. If you want at your own leisure, again, you can read them. One's from Nature and one's from NCBI. And I mean, I don't know how. To be honest with you, when I first came across this talk, well, like I said 5 years ago, thought I would be hearing more about it. I haven't really heard a lot about it. How many of you have heard of this, using electric fields as a cancer therapy?
Yeah, I've never heard of it.
Yeah, I mean, and you guys are pretty damn good students, so I would imagine like most people have probably never heard of this, right? So in terms of, again, I thought I would hear more about it, but I haven't. So I mean, it sounds promising, but I guess just sometimes things take a really long time for them to become put to practice, to make sure that they're safe. I mean, we're talking about making a vaccine for this virus, and they're saying that you might not get one until late next year, right? So I know things take time. I understand that. But anyways, in terms of today, that's all I really wanted to do. I just wanted to introduce electric fields. I want to give you guys a chance to play around with those sims so you can really, really visualize what the fields look like, what patterns they produce. And then on Thursday, we'll meet up again. We'll go over any questions on gravitational fields that you might have. And then we will, next week, we'll continue with electric fields again. Okay?
Okay.
Let me stop the
Okay,
recording. Let
sounds
me
good.
stop the recording right now. Hold on, I'm gonna stop